Assalamu alaikum. My name is Mohammad Tanzim Rashid, and today we'll be presenting inverting amplifier simulation and presentation for analog IC design code EEE4226. My full name is Mohammad Tanzim Rashid, and my metric number is 204928.
My name is Zaki Mohammad Zaki Al-Hashimi, and my metric number is 205039.
My name is Hesham Abdulsamad Al-Dahbali. My metric number is 204715.
Okay, so moving on, at first we'll give you a small introduction on what an operational amplifier is. Operational amplifiers are versatile analog electrical components which are widely employed in electronic circuits. It serves various purposes like amplification of voltage difference between inputs, signal conditioning, and mathematical operations. There are two basic configurations of operational amplifiers, or known as op-amps, that are basically used as substructure for developing complex op-amps. They are inverting op-amp and non-inverting operational amplifiers. So basically, inverting amplifier configuration is set in such a way that the output is inverted compared to the input, and the gain is the ratio between the feedback resistor to the input resistor. As for a non-inverting amplifier, the output is in phase with the input, and the gain is the same as inverting op-amp. So basically in our project we'll be concentrating on inverting amplifier. We'll first create a schematic of it and then move on to simulate the whole thing. Okay, next page. Alright, firstly, some advantages of using inverting amplifier op-amp is that it's very easy to design because the structure is very simple. It's also easy to analyze, so it's very good to use in educational purpose. And also, like because of the flexibility of the configuring part of the whole system, it can be used in various applications and also modified to requirement. Hence, it's also this kind of inverting op-amp are very stable, like especially if negative feedback is used in this kind of situation. And also, a common mode rejection actually refers to the fact that it's very effective in deterring unwanted interference or noise. Alright, so for practical uses, waveform generator, in audio processing, in waveform generators, this kind of op-amps are used to cancel undesirable phase effects that happen. As for robotic arms, or in robotics, the input that is received from velocity sensors are used, are converted to positional signal using inverting op-amps, and this also helps in precise controlling of the position of robotic arm. An inverting op-amp can also be used as a voltage to current converter, so that where the output current is proportional to the input voltage. And for a precision rectifier, this kind of configuration can be used to rectify AC signals with minimal disturbance. Okay, I'll pass it to my partner Hesham, and he will do the rest.
Okay, Zaki.
Yeah, this is Zaki. Okay.
Sorry.
Now, regarding the inverting op-amp circuit, it consists of a ideal op-amp that has its non-inverting input connected to ground. All right, and the input voltage is coming in through the inverting input, where the voltage would be the exact same for the inverting input as the non-inverting input, because in ideal op-amp the voltages for both inverting and non-inverting inputs would be exactly the same. So in this case it would be 0. So the current that flows through R1 would directly continue flowing through RF and continue to V out, meaning that I1 and IF are exactly the same. They are equal to each other. Since VI, which is the input voltage, minus the 0, which is the inverting input voltage, divided over the R1, will equal I1, is equivalent to the inverting voltage, which is 0, inverting input voltage, which is 0, minus the V output, over RF, which is the IF. Therefore, from this formula, we can determine the value of the output voltage using the input voltage multiplied by a ratio of negative RF over R1, meaning that the gain of this circuit is equivalent to negative RF over R1. This means that the output of the circuit would be the input voltage inverted and multiplied by the ratio of RF over R1. Next slide, please. So this is how the input would look like. It would be, for example, if it's a sine wave, it would be the black. It would be the black line in the graph. Okay, and the output voltage would be the red line in the graph, where it's inverted. Every positive peak has a mirrored negative peak, and it's amplified by the value of RF over R1. Next slide. I'll pass it over to Hesham.
So for the circuit development, because we wanted to develop this amplifier from transistor level of abstraction, so this diagram shows the transistor level circuit of the op-amp that we developed. It consists of two parts. So it consists three parts, which is our current mirror here, the differential amplifier, and a common source amplifier. The differential amplifier provides us with a gain, while the common source amplifier connection provides us with the voltage swing. So we will discuss the calculation that we followed to develop this circuit and to choose the correct sizes of the width and length. So the design specifications that we decided to go with is for our current mirror, which is like we choose the I bias to be 100 microamps. The gain bandwidth, which is the frequency which our amplifier will support to operate, is 5 megahertz. And also we have, as we can see, the capacitor at the output of the differential amplifier is 10 microfarad, 10 picofarad. And then we also have the threshold values and the slow ratio, which represent the rate of change of the output voltage. Okay, and then the ICMR, the range of ICMR between 0.9 and 1.7, the minimum and maximum. And we choose our length according to the technology, which is 0.4 micro ohm, okay, micrometer. So at the beginning, to calculate for M1, to calculate it, we needed to get the value Vx, which is between M1 and M3. So we did a simple simple calculation to extract the value of Vx according from Vd more than Vg minus Vt, which is this equation coming from the fact that VDS more than equal VGS minus VT in a saturation mode, because all the transistors within the circuit has to be in saturation mode for the circuit to be operated correctly. So therefore we went with this, and we found that Vx equals 1.15, and then we used we additionally used the slow rate and the capacitor to find our I bias. Okay. So after that, we found to calculate the ID, because ID is going to split between the two branches of the differential amplifier. So we found it as 50 microohms. Okay. And then also we have here VGS3 equals VGS4, because they're both mirrored, and equals VDD minus Vx, which is 0.6 volts. Okay. For this one representing the calculation for the W over L ratio. Okay, so from the equation, the first equation, which is shown here, this is the general equation of the transistor, of the current flowing through the transistor during the while it's operating in the saturation mode. Okay, so from there we extracted the W over L, and we calculated for 3 and 4, as they have they are both mirrored, and they have the same and they are both PMOSes. So we calculate to be 176. For the M1 and M2, similar. We did the same we calculated the W over L using another equation, which is the truss conductance over the current multiplied by 2 multiplied by nu and Cox. We found it to be 4 4 as the ratio. Okay. For M5 and M6 and M7, similarly, we first calculated the ratio. We calculated the range of values which will be operating in saturation using the ISMR, the minimum value of the ISMR, and then we plugged it in to find the VGS1. From there, we got the transistor number 5 drain saturation will operate during saturation, and then from there we found the W over L. Similarly, for M8 is similar, but we used the mu p Cox instead of mu n Cox, and found it to be 115. So this circuit, this schematic represent the whole diagram, the whole circuit with the corresponding each component with this corresponding length and width, illustrated in this diagram from M1 to M8. Okay, and our current source of 100 microamp. So now we'll go to the schematic to show the actual circuit designed in Cadence. We are here in Cadence, so here we can see the simulation. Sorry, we can see the transistor level circuit circuit of our design. It shows all of the component, the PMOSes, NMOSes, capacitors, and the current source, plus the ports, the input and output ports. It shows this part, which is our differential amplifier, and this part, which is our common source amplifier. Okay. Also, so we have connected to VDD and VSS. Okay, which is our power, the positive and negative power. So actually, we can zoom in here to view our. We can look into our component sizing. It follows our calculation and our design. Yeah, we have updated all of the sizing, the width and length of all the component according to our calculation. So I'll pass it now to Zaki to explain the symbol and the simulation part.
All right, thank you, Hesham. Now, after we finish the schematic, transistor level schematic for the op amp, we will be creating the symbol for the op amp, which we created right here. We made the inverting input, non-inverting input, the VDD and the GND or VSS port here, and the output port here. So after we created the symbol, all right, we had to start creating the inverting amplifier test bench, which is found over here. All right. So now that we have the test bench open, we have connected a VDD of 1.8 volt and a VSS of negative 1.8 volt, which is represented by this 1.8 volt voltage source connected in reverse. And since this is a inverting amplifier, the non-inverting port is connected to ground, and the our actual input voltage, which is here, is connected to the inverting port. So in this configuration, we would have two resistors. All right, the one creates a feedback loop where its value is, I'm trying to zoom here, its value should be 2 kilo ohm. Yeah, right here, 2 kilo ohm. All right, and our other resistor would be 1 kilo ohm. So if this is the case, the actual gain of this circuit, since it's an inverting op amp, would be negative RF over R1. So in this case, it will be negative 2 over 1. So the output should be inverse of the input and doubled in terms of its amplitude. So here our input is 0.5 volts or 500 millivolt, right, with a frequency of 1 kilohertz. So now we will simulate and see how the actual output will look like. All right, so in ADE. All right, so we'll be plotting V in and V out. and we'll be simulating in transient for 3 milliseconds. All right. All right, so this is the result of our simulation. Let me just expand it. All right, so our input is represented by the V in red, where we see it is going to half volt positive and half volt negative. So it's VP is 0.5, and our output, which is in green, has a VP of 1 volt. Right here, yeah, it's almost 1, exactly. Meaning that our circuit behaves properly. It is an inverting op amp that is amplifying the output 2 times and inverting it. Since our positive peak is being mirrored and our negative peak is being mirrored, and vice versa. And I think that concludes our simulation.
All right. Thank you for watching, everyone.